In this video, we're going to take a look at some limits at infinity of trigonometric functions. So here, if we were to look at the limit as x approaches infinity of cosine of x, so remember our cosine graph looks like this. So we want to know what value is this heading towards as our x value heads towards infinity. So what value is this settling down on? And if you were to say, it doesn't really settle down, it's not really heading towards any one value, it's between -1 and 1, I would say that's exactly right. This limit does not exist. Because it bounces back and forth between -1 and +1, it's never actually settling down on any one value. As our x value gets really big, you aren't getting as close as you want to any one value. Great. On this second example, here we have the limit as x goes to infinity of cosine of x divided by x. So when we look at that, this cosine of x, it bounces between -1 and 1. This value of x is getting really big. Really large. So if we take some number that is somewhere between -1 and 1, and we are to divide that by some giant number, right? So divide that by 10 billion. Right? So -1 divided by 10 billion. It's going to be a negative value, but really close to 0. 1 divided by 10 billion is a positive value, but really close to 0. And anything between -1 and 1 divided by 10 billion is going to be something close to 0. No matter what the top happens to do, ultimately you have the denominators getting large, and so this thing is heading towards just 0 itself. So those are some limits at infinity of some trig functions. Now we can also have infinite limits at infinity. And so here, let f be a function defined on an interval from 0 to infinity. The statement, the limit as x goes to infinity of f of x is equal to infinity, that means for every positive number m, there's a corresponding positive number n, such that if f of x is greater than m, whenever x is larger than n. Right? Basically, we're saying that our function can be as large as we want as long as our x value is sufficiently large. And we can make a similar statement for limit as x approaches infinity of fx being equal to -infinity. It tells us that there's a negative number m and a corresponding positive number n, such that our function is sufficiently small. So our function can be as small as we want whenever our value of x is sufficiently large. And then you can give similar definitions for x heading towards -infinity and having outputs of either -infinity or positive infinity. All right, so let's look at a quick example here. Here we have the limit as x approaches -infinity of x squared. If you were to think about y equals x squared, that's the graph of a parabola, right? So we have this parabola. As our x value is heading towards -infinity, so our x value is getting really, really small, what's happening to the y value? Well, it's just getting larger and larger and larger. So this limit, we would say, is infinity. Excellent. So let's look at 2 more examples. So here we can use long division to find an infinite limit of a rational function. So here we have a rational function, 2x squared minus 4x over x plus 1, and we want the limit as x goes to infinity. So we'll do long division, x plus 1 going into 2x squared minus 4x plus 0. We ask ourselves, what do I need to multiply x by in order to get 2x squared? We have to multiply that by 2x, and then we do that multiplication. So 2x times x, I said 2x, but I wrote 2x squared. 2x times x gives us 2x squared. 2x times 1 gives us 2x. So we did this multiplication where we multiplied this by the x, and then we multiplied it by the 1. And then we switch the signs. So we will subtract those. So now we have negative 6x plus 0. And then we do the same thing. So what do we need to multiply x by in order to get negative 6x? We have to multiply that by negative 6. And then we do that multiplication. So negative 6x minus 6. Change the signs and combine. And now x is larger than 6, and so we have a remainder of 6. So we can say plus 6 over x plus 1. So that's the long division. And so now this limit over here we can rewrite as a limit as x goes to infinity of 2x minus 6 plus 6 over x plus 1. The 2x as x goes to infinity, that's heading towards infinity. All right, so that's going towards infinity. The next piece is just going to stay at 6. And then this piece here, as x gets really large, 6 divided by some really large number plus 1 is going to be really close to 0. And ultimately, we just get infinity itself. Right? So that limit is heading towards infinity. If we are to look at the limit as x goes towards negative infinity, this was the same function, so again we have 2x minus 6 plus 6 over x plus 1. And if we did substitution, you'll get negative infinity minus 6 plus 0, which is negative infinity. So that limit heads towards negative infinity. Perfect. So we did some long division over here. And then after we did that long division, we were able to find our limits. Fantastic. So in the next video, we will look at some more general guidelines and observations we can make when we are looking at limits of rational functions, some observations that will make our life a little bit simpler. We will see you in our next video.